Hello, here is the user's guide on sources. Here you can see the sources. This is a AC voltage source. This is a AC current source. This is a positive DC source. This is a negative DC source. Here you have a triangular source, square source. Then here we have a lightning current source. Then we have a three-phase source. I will go through the sources one by one. Here we have a single phase voltage source connected to a resistor. If I double click, I get the entry mask, and let's say I can adjust my source to 100 volts. I can watch the voltage, the current and the power. Let's see what happens. You see, this is the voltage. The blue curve is the voltage, the green curve is the current, and the red curve is the power. You will notice that the red curve is negative because the power is leaving the source, so it's negative. And the current is also 180 degrees phase opposition to the voltage. This is because the current is leaving the source. If you're looking at the resistance and I'm checking the current and the voltage at the resistance and do not measure these element values at the source, this is the picture you get. So you see that in this case the current and the voltage both are on each other, and if I'm checking the power at the resistance, you will see that the power in the resistance is then counted positive. So this is the power seen from the source, and this is the same power but seen from the resistance. When the simulator is running, then I can change the phase angle of the source. The phase angle of the source can also be changed on the input mask here. Here I want to demonstrate what you can do with this phase shift I have been addressing just before. You can simulate the power exchange between two sources. So here I have the two sources, 10 kilovolt each one, and then I have some inductor and a small resistor to prevent a DC component to stay forever. Now you can see here I have leading voltage in this source compared to this one. That means that I generate power in this source and I feed power into the other source, which is lagging. And you can see that the power at this source is negative. That means it supplies power. So does the current. If I change now from leading to lagging, you can see how the power is now fed from this source into this one. So this power is now positive. This is how you can play around with the phase angle of the source. There is also a triangular and a rectangular voltage source. You can also use the single phase voltage source as a single phase power generator. Then you can go here, you push the tick box generator, and what you see now is that you have to enter the maximum power. In this case I choose 100 megawatt, and then automatically it calculates an inertia. The inertia is normally shown here. You can change it, of course, and then let's run it now to see what happens. The first thing you see is that you get a frequency meter here. And if we let it run, we can also see now how the frequency changes depending on the amount of power you supply. So here you control the power, and here you control the voltage. Now you see that I do not consume enough power, so the frequency goes up, so I have to reduce the resistance to increase the power consumed by the resistor, and then you see how the frequency goes down. If the frequency goes below 50 Hertz, I may have to adapt it again. So I control the power output, and then the frequency will go up again. So this is a simple generator, and you can observe how the equilibrium between power generated and power consumed at the load is kept in a balance. Controlling the balance between power generated and power at the load can be quite difficult, especially if you have more than only one source. And therefore in a generator normally you have a droop, and the droop is controlling the frequency by controlling the power. So this is the droop checkbox, and as soon as you have the droop checkbox ticked, it will be much easier to control the frequency. the power output will be controlled accordingly. So you can see, even if I push my power output, the real power delivered from the source to the load is limited by the frequency control. And this is exactly what also happens in a real power generation station. So the drop helps to keep the balance between generation and load. And by the way, the power output slider here adapts the torque applied to the generator. So it's kind of a torque regulator. You can also use the generator as a storage unit. In order to get the storage ready, I just push the tick box for storage. Of course, the tick box for generator must be on as well. And then I put some megawatt hours which I want to store. So the storage capacity is, in this case, let's say 0.3 megawatt hour. And let's run it now and let's see what happens. So now I use the storage. You can see how this red bar is decreasing over time. And if I want to fill the storage, I need to use the source as a motor. Now you can see how energy is pumped from this source here into the generator, into the storage. And you see now how the storage capacity is filled. And once the storage capacity is fully filled, there is nothing to store anymore. You can also use the voltage source as a renewable power generator, like for example a wind generator. To do so, again, you double click on the source and you tick the renewable checkbox. And then here you have to enter a value in seconds. Every, for example, in this case, second, every 2 seconds, the torque of the renewable power generator is randomly changed. And this will be the effect. Let's run it. You can see now how the level of the torque is changing randomly every second. And you see how this affects the phase angle between the grid and the power generator. Here I want to demo the 3-phase voltage source. Everything you just said for the single-phase source is also applicable for the 3-phase source. There is, however, one exception. You see that on one of the phases there is such a dot. So we have the 3 phases RST, and the dot is on the R phase. And if you interconnect more than one source, you have to make sure that the dot is always on the same phase. So you see, for example, if you now right click on this source, you can either flip or rotate the source. If you rotate the source, this is what happens. And if you want to now connect these sources to each other, for example, you have to make sure that the same phases are always connected to each other, otherwise the model will not work. So if you want to flip it, you right click on it and then you flip, and you see now you have the same phases on each other. You can also flip the phases if you go to the entry mask, to the input mask, and you flip it here, so it has the same effect. So you can flip it here, the entry mask, or here. Flip, flip. There are 2 types of sources with a small little difference. So in this source here, the RST phases are connected by the neutral, whereas here they are not connected. If you want to have the same source from here and here, you would have here to interconnect the neutral, and then they behave exactly the same. If not, you can series connect the 3-phase source to another source, and you are much more flexible. But normally you will most probably use only this source here. Another important difference between single phase and 3-phase is the traces. You see that here you have a 4th trace. So if you keep the trace P, then you will see that you get power output for each and every phase individually. However, if you push instead of the P, you go to the G, you get the sum of the power output, and this is a straight line as you can see down there. If the circuit is balanced, meaning that the power of the load is equal for each one of the phases, then the reactive power of the three phases neutralize each other, and therefore the remaining straight red line here is the sum of the active power. You can also roughly model the transient subtransient behavior of a generator. As long as the generator tick box is off, you get access to this transient and subtransient, where you have to input the power of the machine, three-phase, and then in percentage P values you have to add these ones, and then you can run such a simulation and you get the transient short circuit currents. There is a lightning current source model for insulation coordination studies. There is also a steep wavefront lightning current simulator for insulation coordination studies. The input needed is the peak in kiloamps of the lightning current and the time when you want a stroke to happen after initiation of the simulation. Test all the source filters yourself. Go to www.ecsp.ch.